Hi guys, I'm Simriti Agarwal from Gauge How. We are back with a brand new video about geometric dimensioning and tolerancing. In engineering, dimension measurement deals in design, manufacturing and inspection. In design, there is an ideal form of the product with a specification. This specification is used to design the product called the workpiece, and the workpiece is a real form of the product. Now, we will have to measure it. In measurement, we inspect the workpiece by the reference of specification given in the design of the product. As we know, it is impossible to manufacture the exact dimension of the product every time, so we try to manufacture a product within tolerance. Tolerance is the difference between the permissible upper and lower limits of the workpiece. In other words, tolerance is the limit of the deviation allowed in the final workpiece from the given measurement in design. During inspection, there are two factors which decides whether the manufacturing product is accepted or rejected. The first is tolerance and the other is geometry. For example, in the inspection of a circle having diameter of 27.5 mm with tolerance of 0.5 mm, the first product is a pentagon, so it does not qualify because it does not satisfy its geometrical tolerance. On the other hand, the second product satisfies its geometrical as well as dimensional tolerance, so this product is accepted. This use of dimensional and geometrical tolerance in combination is known as geometric dimensioning and tolerancing. There are many standards of geometric dimension and tolerancing, like international and national. However, the most common is ISO, or International Organization for Standardization. Engineering drawing is usually presented in first angle orthographic projection or third angle orthographic projection. These orthographic projections can be further explained as follows. A three-dimensional space can be divided into four sections. The observer always looks from the right side. In first angle projection, the object is kept in the first quadrant so that the object is between the observer and the plane of projection. Whereas in third angle projection, the object is kept in the third quadrant so that the plane of projection is between the observer and the object. These are the symbols by which first and third angle projections are represented. Points of drawing in space can be specified through coordinate systems, which uses one or more numbers or coordinates to do so. There are three types of coordinate systems. First is Cartesian coordinate system. This system has three perpendicular orthogonal axes known as x, y, and z. The point of intersection is known as the origin. The second type of coordinate system is the spherical coordinate system. In spherical coordinate system, the location of the point is specified by the coordinates r, theta, and phi. The third type of coordinate system is the cylindrical coordinate system. In this system, the location of the point is specified by the coordinates rho, phi, and z. Here we can see that the Cartesian coordinate system uses three distances, spherical coordinate system uses one distance and two angles, and the cylindrical coordinate system uses two distances and one angle. Tolerances, as discussed before, are shown in the drawings. The tolerances on the dimensions can be specified in three ways: unilateral tolerance system, bilateral tolerance system, and limit dimension system. In unilateral dimension system, the tolerance is provided only on one direction from the basic size. For example, in this rod, the tolerance is given only on the positive direction, which is 20 plus 0.3 to plus 0.5 mm. We can say that the maximum and minimum permissible length of the rod is 20.5 and 20.3 mm respectively. In bilateral dimension system, the tolerance is provided on both directions from the basic size. For example, in this rod, the tolerance is given on the positive direction as well as the negative direction, which is 20 plus 0.3 to minus 0.5 mm. In the third dimensioning system, that is, the limit dimension system, The size and deviation of the part are specified by only the maximum and minimum dimension. For example, in this rod, the tolerance is given as the lower limit to be 20.3 mm and the upper limit to be 20.5 mm. Datum and degree of freedom. A datum is a virtual ideal plane, line, point, or axis. It is used as a reference for other features. There are three kinds of datum: primary, secondary, and tertiary datum. Degree of freedom, in very simple terms, is the number of directions of motion possible for a body. A rigid three-dimensional body, like cube, has 6 degrees of freedom. Translation along x direction, translation along y direction, translation along z direction, rotation about the x-axis, rotation about the y-axis, and rotation about the z-axis. In geometric dimension and tolerancing, a tolerance frame or feature control frame is required to describe the conditions and tolerances of a geometric control on a part's feature. The feature control frame consists of 6 pieces of information. The first is arrow. This is used to represent the area of the technical drawing. The second is geometric symbol. Here it represents a hole. Tolerance value. In this example, the tolerance value is of 0.1 units. Shape symbol. It is diameter in this symbol. Feature of size or tolerance modifiers, and datum. The symbols used in this tolerance frame can be divided into 5 categories, namely form, profile, orientation, location, and runout. These symbols are standard, that means they are used all over the world. Under the form category, there are 4 symbols, which, as the name suggests, describe the form of the part of the workpiece. The 4 forms are straightness, flatness, circularity, and cylindricity. In profile, there are 2 symbols, profile of a line and profile of a surface. Orientation has 3 symbols, angularity, perpendicularity, and parallelism. In location, there is position, concentricity, and symmetry. And in runout, there is circular runout and total runout. Now you may ask, what is runout? Runout is an inaccuracy of rotating mechanical systems, specifically that the tool or shaft does not rotate exactly in line with the main axis. For example, when drilling, runout will result in a larger hole than the drill's nominal diameter due to the drill being rotated off-axis instead of in line. Some other common symbols used in a tolerance frame to specify a feature's description, tolerance, modifier, and datum references are free state symbol, least material symbol, maximum material symbol, and projected tolerance zone symbol. These symbols specify some conditions which would be necessary in the making of the workpiece. For example, the least material condition describes a dimensional or size condition where the least amount of material exists within its dimensional tolerance. That is, for a shaft, its diameter will be the smallest permissible, and for a hole in workpiece, it will be the largest permissible. The maximum material condition is the opposite of this. It describes the feature of a part where the maximum amount of material exists within its dimensional tolerance. So, the shaft diameter will be the largest and the hole will be the smallest permissible. A symbol is added to the drawing with necessary information which specifies how the workpiece must be formed and finished. This symbol is the basic symbol of surface finish specification. It specifies the surface which needs surface finishing. Here, the presence of top line on the triangle indicates that material removal is required. If the line is replaced by a small circle, then material removal is not required. In other words, first symbol shows that machining is done on the surface and the second one forbids it. A surface finishing symbol specifies information like surface parameter specification, lay orientation, and required minimum material removal. Now, let us try to read a control frame. Let us consider